All right, everybody. Hello. Another fun episode in our study of our wonderful and amazing dynamic planet. And perhaps one of the most dynamic elements of this planet is related to the formation and the movement and the erosion and the deposition caused by ice being on this planet, solid water on this planet. And we're going to learn that the amount of solid water on this planet has most certainly varied through time as Earth's climate has evolved, and that tracking that movement can give us really interesting insight as to how the Earth system works. And in that uniformitarian approach that we've been applying throughout the semester, the present is the key to the past. We can look at our modern glaciers. We can look at the structures that they generate, that exist around them, making some really important interpretations regarding this planet's past climate history and what we might predict this planet's future climate to be like as well. So certainly an important topic here, and a fun one as well. So what are our objectives? Well, we're going to talk about the different types of glaciers that we see around the world and how they form. We're going to talk about how glaciers move and the landforms that they generate by that movement. And then we're going to talk about, again, the natural climate cycling and how climate has varied through time to make these glaciers go through periods of advance and retreat. So lots of fun ahead. Let's get after it. So our types of glaciers, we can really separate out. There are two general types of glaciers. Those are alpine glaciers and continental glaciers. Alpine glaciers can exist anywhere in the world, typically where you get lots of high elevation mountains. So here in California, we most certainly have glaciers. They are alpine glaciers located there largely in the Sierra Nevada mountain range. We have a few of them. They're much smaller than they've been in the last few thousand years or so, but they are indeed there. And these are mountain glaciers, alpine glaciers. These are different than our continental glaciers, right? Where continental glaciers, the extent of these huge bodies of ice that can extend across large portions of continents, their presence, their size is very much dictated by global climates, global climate related factors. And so currently we have only two of these continental glaciers, one in Greenland and one in Antarctica. These are massive bodies of ice that cover huge amounts of land. So very much different than what we see in our alpine glaciers, where typically altitude in our alpine glaciers is going to have a huge impact on the presence or absence of these alpine glaciers, whereas continental glaciers, the extent of those glaciers largely being controlled by changes in global temperature rather than just surface height there above sea level. All right, so those are our two main types of glaciers. Let's talk about how a glacier forms, right? To form a glacier, you got to have snow, right? That might seem intuitive, right? Well, yeah, of course. To make ice, you got to start with some frozen water, right? Yes, absolutely. But it's really important to recognize that it's not just you need snow. You actually need that snow to stick around for a really long time. I'll mention that particularly in areas near our poles, precipitation levels are relatively low. Atmospheric circulation results in relatively low levels of precipitation in those areas. But when it does snow in those areas, that snow sticks around for a really long time. Snow falls as snowflakes, right? What happens is as those snowflakes age, they start to undergo some serious change. That is, as those snowflakes age, their shapes change, their consistency changes from first snowflake to then you get your granular snow. If you've ever been to the mountains, maybe a little while after a snow, you might have felt that the snow feels kind of like almost like slushy ice, right? It doesn't feel nice and light and fluffy and flaky anymore. And what you're seeing again is that transition from that snowflake to that granular snow and eventually firn, right? So firn is essentially that kind of small little particles of ice. Through time, as that firn is compacted and forced together, that will eventually form glacier ice, right? And so what you really need to do is let that ice sit for a while in order to form a glacier. And generally that's going to take a few years. May take 2 years before you get snowflakes turning into ice that actually contribute to a glacier, which means that you need snow to fall on these continents or in these alpine areas, and then you need that snow to sit around and not melt. You can't allow those temperatures to rise to where that stuff melts in order for those materials to contribute to the glacier, right? And so that contribution there happens in a really distinct area. This is called the zone of accumulation, the zone of accumulation, right? This is where, again, this stuff is falling and then persisting for oftentimes a few years in order to contribute to that glacial ice. So generally, the zone of accumulation, the base of that zone is defined by the permanent snow line. That is the year-round snow line. That is, if you were to look up at the mountains in July and see that there was still snow at those peaks, then you are potentially within that zone of accumulation. All right, so this is what this system looks like for an alpine glacier, at least, right? That is the higher altitude portion of the glacier, right, is going to be that area that is defined as the zone of accumulation, right? The base of that zone there, right? So here's our zone of accumulation. The base of that zone there being that permanent year-round snow line, right? This is where things get a little bit interesting, right? The glacier itself obviously does not just exist within that zone of accumulation, as we can see in this image, right? It exists, that glacier exists well down below that snow line. That glacier may even may extend to levels all the way well below anywhere that it might snow. So how does that work? Well, it works because these glaciers are being driven forward and down slope by accumulation within that zone of accumulation. That is, if we imagine that this glacier was not here, right, and we had this zone of accumulation, snow would pile up there, it would become ice, right? And with the filling of this zone of accumulation, you start to have enough force to actually drive the glacier down slope. Glaciers are made of, or that frozen water that these glaciers are made out of generally has what's called a high albedo. That is, they are highly reflective. When you look at that ice, it will look very white in color, and that's because it's reflecting all of that light off of it. Once that ice forms, it's pretty hard. It takes a lot of energy to melt it back down, which means that it can be driven down slope over a significant distance. So what starts to happen is this ice, right, being pushed behind by additional accumulation here in the zone of accumulation, that ice will begin to move down below the snow line. That ice is flowing, and we're going to see in a somewhat plastic behavior, right? Kind of like if you imagined a really, really viscous, really thick glue or syrup, right, flowing down this canyon. This is like really, really, really thick syrup or glue that would take many years to flow, but it is absolutely flowing. And so that glacier will flow and flow and flow and flow and flow until eventually it reaches a point where temperatures are high enough where any additional accumulation is not enough to further extend that glacier out from the canyon that may contain it. This is what we call the zone of wastage. The zone of wastage here. This is where the zone of wastage, right, is where we see these glaciers actually shedding their ice, right? That ice is melting, right at the end of that glacier. That is the zone of wastage, right? So this is the end of the glacier. And again, that is speaking to that balance between the physical properties of the ice itself and the surrounding temperatures, as well as the rate of accumulation within the zone of accumulation of the glacier. So with that said, we can think about these glaciers as kind of representing a budget of sorts, right? When you look at the length of a glacier, when you look at the thickness or volume of a glacier, you're looking at a really delicate balance between how much ice is accumulating, right, and how much ice is being wasted. That is, during times when you have more accumulation than you have wastage, that glacier will extend. It will go farther, right, than it would in a balanced scenario. When wastage exceeds the rate of accumulation, the glacier will actually retreat, right? It'll retreat. It'll go back up slope. It'll get shorter, right? Because you're getting more wastage than you're getting accumulation. So let's think about that for a minute. Well, what can impact either accumulation or wastage, right? Well, accumulation, the rate of accumulation, right, is going to be dictated by how much snow is falling in those areas and how much of it is sticking around throughout the year. That is, where is that snow line, right? What's the size of that zone of accumulation? Under very cool time periods, when you might get lots of precipitation in some situations, right, then that zone of accumulation is going to be larger because ambient temperatures surrounding the glacier are low, and thus the snow line extends a little bit lower, right? So bigger zone of accumulation, higher levels of precipitation, right? Higher snow levels result in more accumulation, which means, again, more being added to the glacier, right? Those cooler temperatures also will reduce the amount of wastage that's happening, right? If things are cooler, if ambient temperatures are cooler all around the glacier, right, the glacier will not find that balance, right, where it starts to shed that ice until it reaches further away from that zone of accumulation. So during times of, during cool periods and during periods of high precipitation, either or both of those factors can contribute to a glacier extending itself, right? To glaciers getting bigger. What about retreating glaciers, right? Well, if we reduce the size of that zone of accumulation, right? Or we reduce the amount of precipitation, right? Then we reduce the size of that zone of accumulation, right? By moving the snow line further up in elevation, right? So that zone is made smaller and it's also receiving less snow. So there's less going into this system. Those warmer temperatures also will impact that portion of the glacier within that zone of wastage. And thus we'll get more melting. And this is why we'll see these glaciers retreating. So looking at these glaciers, we've got this great sort of thermometer, right, that's responding to these changes in their environment all on their own through these natural processes. And that's why looking at these glaciers can give us a great opportunity to evaluate how different areas may be responding to potential perturbations or changes in global temperatures and global climate. All right. So again, great indicators of those changes. All right. So as I mentioned, these glaciers are not static. They indeed move. This ice moves, right, from that zone of accumulation to that zone of wastage. And so how are they moving? Well, they're moving in two ways. one, the entirety of that ice is sliding a little bit on the floor of the canyon or the land surface that contains it, right? That is that small amounts of melting at the base of the glacier may lubricate portions of the base of the glacier and help it to slide. But I will note that that sliding component of a glacier is much less significant than the internal flow of the glacier itself. That is, when you look at the total movement of a glacier through some period of time, right, we see that a small portion of that is the actual just sliding of the glacier itself, right? The majority of that movement is that internal flow. And this is a great graphic that I think illustrates that internal flow. And that is that the ice itself, right, while a solid, will flow plastically, particularly in the central portions of the glacier, right? So just like our rivers, right, the fastest flowing portion of a river is right in the center of that river, just below the surface. Very much true for ice as well. And that's because this is the area of the least amount of friction, right, between that ice and its surrounding environment. And so you can see here, there were stakes put into this glacier and tracked over a series of 8 years. And we could see that those stakes had moved some distance by basal sliding of the glacier, right? So all of these stakes had moved collectively together. But again, these central stakes here had flowed a little bit further. And that's because of that internal sliding or that plastic flow associated with this glacier as well. All right, so they are moving. And again, that is taking those materials from that zone of accumulation to that zone of wastage. And this ice is really, really, really capable of shaping its environment, both through processes of erosion and deposition, right? So because these massive amounts of ice can move, they're actively eroding as they do so. The ice itself, right? The ice itself might do a little bit of grinding down of rocks and polishing rocks as it moves across them. But I will note that what's doing a lot of this erosion is actually performed by the sediments and the rocks that these blocks of ice they carry. That is, a glacier is exposed, it's open to the surrounding environment, which means that rocks that fall onto that ice, dust and sand particles that fall onto that ice, those same particles that are maybe entrained in the flow of ice as it moves from high elevation to low, that is like taking a piece of paper and gluing some sand to it and making some sandpaper, right? That glacier containing those materials can move across the landscape and utilize those materials, and those materials actually result in then etching the surrounding landscape. And so we see some really interesting features associated with the movement of both the ice and the sediments that it's carrying, right? That are really diagnostic in evaluating areas that may have been exposed to glacial movement in the past. So you see on this rock here, you can see maybe these parallel grooves on this rock. These are called glacial striations. And these glacial striations are going to be made by small rocks and particles and debris present at the base of the glacier as it moved across this rock surface, right? Those particles would have drug right through this rock and etched these grooves in the surface of this rock. You can utilize these striations. Sometimes they'll change in their depth. Sometimes they'll suddenly appear in the surface of the rock and drag for some distance. We can utilize these striations to not just diagnose that glaciation was present, but to be able to say some really impactful things about the way these glaciers moved that created these striations. Their direction of movement can be indicated by these striations. Another really distinctive bit of evidence of glacial activity are polished surfaces. And so looking across, if you've ever been to Yosemite, the Yosemite Valley, you'll see lots of these polished and striated surfaces. And so this surface here, nice and shiny, you can actually also see some striations in here as well. But this nice polished surface here, just like you would polish maybe a piece of metal or something, right? Those abrasives contained within that ice moving their way across the surface can polish it, can make it really, really smooth. You want to be careful walking across these. They can be really slippery, especially if there's been a recent rain or something along those lines. These polished surfaces are very much polished. They're really, really smooth. And so, but again, indicative, paired with our striated surfaces, really indicative of landscapes carved by glacial movement. But maybe the most distinctive and wide-reaching features of generated by glaciation has to do with how they shape the general landscape that surrounds them. Water is a very powerful tool in weathering and erosion. Water in liquid and solid state does a lot to shape the landscape. However, water in liquid versus solid state shapes the landscape in very different ways. A general rule of thumb is that the low points generated by a glacier will have a much more rounded appearance than the low points generated by moving liquid water. We're going to see what I mean by that here in just a minute. The high points generated by a glacier can be very sharp, can be very pointed, right? And some of that has to do with the movement of glacial ice, but it also has to do with some of the activity involved in things like frost wedging and things that serves to break rocks apart, fracture them, oftentimes in unvegetated landscapes that can leave these very sharp angular peaks and things, right? So this landscape here identifies some of the features created by a glacier and calls out some of the terms that apply there. So a horn, if you've maybe ever been to Disneyland, right? The Matterhorn, right? A horn, right, are these peaks, oftentimes surrounded by these flat fronts here, coming to a pyramid-shaped peak. That is a horn, right? That is a horn. Sometimes surrounding these horns or in adjacent canyons, you'll see these bowl-shaped features. These are really key in our zone of accumulation. These are called cirques. And this is where a lot of that snow will accumulate that feeds the glaciation that happens thereafter. Glaciers might be separated by very sharp ridges. Here, these sharp ridges, they're called arêtes. That's called an arête. Glaciers oftentimes do not just show up as a single body of ice, rather kind of like a river, or a lot like a river, where you have maybe a main river channel. That main river channel may be fed by several tributaries that feed into that river channel, right? Smaller creeks and streams that feed into the main stream or river. Same thing for a glacier. And that is that you might have a main glacial body, but then you have these additional glaciers that are coming into the system, right? And coming into the system here, that main glacier is doing very similar things, right, as we're seeing with these adjacent glaciers, albeit maybe in a different direction, which can actually take and erode those ridges that were otherwise spilling towards the valley floor, creating these so-called truncated spurs. As these adjacent glaciers come in and join the main glacier, oftentimes what we're going to learn that they bring with them are huge volumes of sediment, particularly along the margins of these glaciers. So-called lateral moraines can be produced as a result of those sediments. But as these sediments come in and join the main glacier, you might see these rows of sediments then entrained in this main glacier. These rows within the main glacier, we refer to those as medial moraines. And we're going to see that these medial moraines and lateral moraines, these sediments that are carried along the margins of the glacier, once these glaciers retreat, they can actually be deposited as significant volumes of rock and sediment. They can build up to pretty incredible elevations. We'll see some examples of that here shortly. All right. So to compare and contrast, then this landscape, right? This landscape here with one that's generated by a river. Again, I want to note that one of the most distinctive features is that in the canyons, right, of a river valley versus a glacial valley, those low points, our river valleys are going to have a much more V-shaped floor, much more V-shaped shaped floor. Whereas in our glacial environments, we're going to see a much more U-shaped form, right? A much more U-shaped form. And that's because that erosive energy, right, of that glacier and that glacial movement is spread out across that entire canyon floor, right? It's most significant in the middle because that's the thickest portion of the glacier, right? But it's certainly that glacier is moving through and eroding that entire canyon, whereas that erosive energy for our rivers is commonly focused within that lowest point, right? Within the base of that valley floor, all of that energy is focused. So you get that V-shaped valley in an unglaciated topography versus that U-shaped valley that we see in a glaciated topography. And we can see that here, right? We can see that nice U shape here in this glacial valley here from your textbook. Again, nice wide valley with this U-shaped floor. We also see some lakes and things in here. Lakes inside of our glacial topography are also really common. We're going to learn that the retreat of glaciers can deposit sediments, can deposit ice, things that can shape the canyon. That can shape the ground surface and create low spots or spots that have been naturally dammed by these deposits such that water can build up behind them. All right, so lakes in these environments, really common as well. And so just to summarize some of the features that we just mentioned, right? So some of the landforms created by this glacial erosion, so that we have this both in picture form and in text form definition. So a cirque, a bowl-shaped, right? A bowl-shaped area generally within that zone of accumulation that's open on the down valley side, right? That is, the ice is moving from this cirque down valley. I'll note that we just mentioned lakes, that sometimes when these glaciers go away, within these cirques, you have one of those low points, right? And so sometimes you get lakes forming inside of these cirques. We call these tarns. So a lake located in an iceless cirque is called a tarn. And there are actually examples of tarns in our local mountains, in our San Bernardino mountains there. The San Bernardino mountains there, likely housing some glaciers a few thousands of years ago. Fjords, right? Fjords are glacial troughs or valleys, right? They're actually flooded by sea level rise, right? So when a glacier makes its way all the way to the ocean, right, and then starts to, that wastage exceeds the accumulation, so that glacier starts to retreat, sea level rises and fills that valley. That's what we call a fjord. And a arête, again, one of those sharp edged ridges, right? And then our horns are our pyramid like peaks. So the next time you visit Disneyland or drive by Disneyland and see the Matterhorn, you can entertain everybody with stories of glaciation. They probably won't be too excited, but you need something to talk about in line for the Matterhorn. That line can take a considerable amount of time. So if you're looking for something to chat about, there you go. There you go. All right. So again, I wanted to make sure that everybody had access to some of the figures in the textbook that I feel are really beneficial. And so here's a great summary of a lot of what we've talked about sort of together. There's one more example here in this image that I'd like to mention, and that is a hanging valley. When these glaciers retreat, they leave behind these big U-shaped valleys. These contributing glaciers, with being less significant than that main glacier in terms of their size, the canyons that they'll erode will typically be not as deep as that canyon from the main glacier, which means that these canyons can sit up kind of high in the landscape adjacent to this main glacial trough, which results oftentimes in these waterfalls that can come out of these U-shaped valleys. Those waterfalls, or that condition, is what we call a hanging valley. And most certainly there's some tremendous examples of hanging valleys in the Sierra Nevada, particularly in and around the Yosemite area. It's pretty cool. If you haven't had a chance to go to Yosemite, I can't recommend it highly enough. It's an awesome, awesome place. You most certainly have to be mindful of when you're going, time of year, and all that other kind of stuff, because it does close and it snows really heavily, and sometimes there's fires and all sorts of things. There can be large crowds and all kinds of stuff, but it really is a remarkable spot, and a place that we go on our field trips when we have the opportunity to go there. And so something to keep an eye out for there too. All right. So after all of the erosion, what happens, right? We've talked a lot about the ice kind of shaping its landscape by removing materials, but I have noted, right, that these glaciers are carrying with them huge amounts of sediment, right? This is what that can look like, right? These lines that you're seeing here, these medial moraines and lateral moraines that we're seeing here in this this image, those are all rows, row upon row of enormous volumes of sediment being carried by that glacier. We refer to these bodies of sediment as glacial till, glacial till. And glacial till is generally unstratified and unsorted. What does that mean? Well, it means that this stuff consists of anything that could have fallen on or been picked up by the glacier: boulders, pebbles, cobbles, sand, silt, clay, you name it. All of these different sediment sizes, different types of rocks, anything that the glacier encounters can be carried by it. As that glacier carries those materials, right, it's doing so in really with no objective process, right, in selecting which materials are carried where in the glaciers. That means grains of sand may be right next to grains of, or clay minerals might be right next to big boulders, right? Such that when that glacier melts and retreats and deposits those materials, it doesn't do so the same way that sediments might be deposited in the water. That is, if you take a pile of mixed sediments and you put that into the water, right? If you imagine we had a bucket or maybe a 2-liter bottle that had a bunch of different size sediments in it, we filled that with water and we gave it a shake, the first stuff that would fall to the bottom would be the large grain sediments, right? And then they would get finer and finer as time went on, right? Maybe creating some layered sediments there through that process. Glaciers, not so much. When they melt, they just drop it all at once, which means that this stuff is somewhat mixed up. That's what we mean by unstratified. It's not layered, right? It's all just sort of a massive pile, just as you took a truck full of this stuff and dumped it on the ground, right? That's glacial till. There's no sorting, right? There's a whole bunch of different grain sizes, right? So it's not layered, it's not sorted, it's just a big pile of sediment. And those big piles of sediments, right? Those big piles of sediments can result in some really interesting features. I want to mention that maybe the most distinctive feature, or something that we see and utilize to identify evidence of glaciation most distinctly, are what we call moraines. You've heard that term used already a few times, right? And so what you see in this image here are moraines generated, right? Moraines generated by a glacier reaching its furthest reach and then melting and retreating. And so when that glacier reaches as far as it can, right, that zone of accumulation, that zone of wastage pushes that glacier as far as it can. When it starts to retreat, all of that sediment that's at the end of that glacier will be deposited at the end of that zone of wastage. That furthest moraine that's generated, those piles of sediments being that moraine, that furthest moraine, we call that the terminal moraine. That is a terminal moraine. As a glacier retreats, that will take a long time. And through that time, that glacier's retreat, it may oscillate a little bit, right? It may fluctuate, right? That is, it's not just a steady retreat. Once it's moving back, it's just on its way back. Rather, there may be some oscillation there, right? It may decide there may be a period of cold temperatures and high precipitation to where we get a little bit of advancement of the glacier and then it retreats again. You can do that several times. But in each of those times, it's going to generate a new moraine, right? It's going to generate a new moraine. That new moraine that is further or closer to the source, so that zone of accumulation there for the glacier, we would call that a recessional moraine, right? So tracking the locations of these terminal moraines and recessional moraines can give us an indication, a great indication that not only where there are glaciers in this area, but how big those glaciers may have been, and any perturbations in climate that might have happened following the initial retreat of the glacier. All right. So I wanted to show you a few examples of these terminal moraines. These are absolutely massive piles of that glacial till here that you're seeing at the ends of these glaciers. I want to note that you're also seeing moraines here extend along the sides of this glacier down here. We would refer to those as lateral moraines, right? So that sediment that's falling on the margins of the glacier can be really significant, right? And build up its own pile of sediment again as that glacier retreats. That would be a lateral moraine. To give you an idea of the scale of the moraines generated by this process, right? This is an area, a map showing our Great Lakes region, right? And you're looking at maps of moraines, right? Maps of moraines during recent, geologically recent glacial events that extended or had ice extend well into what is now the continental United States. So our Great Lakes, right? Our Great Lakes, the result of the movement of this ice and surrounding those lakes in the area are huge deposits of sediment left in the wake of the glacier, of the glaciers that move through this area. Several of the islands that we see off of the East Coast there, so in areas like Cape Cod or Long Island, those islands are built around moraines. Again, those glaciers that we just mentioned, they're extending down through this area and depositing such massive amounts of sediment, enough to where those sediments are now are up above sea level, and further sediments can accumulate around them, speaks to how massive these continental glaciers once have been on this planet. So these moraines, terminal moraines and lateral moraines, these are direct evidence of past glaciation. And we'll show you one more type of moraine, another one that we discussed earlier, these medial moraines. So these moraines that are present within the central portion of a glacier. And generally that's going to be caused by glaciers converging on each other, which is what we're seeing here in this image of Mount McKinley. We're seeing these medial moraines here, these moraines within the main glacier here, right? These moraines in the main glacier here that are medial, that are within the interior of the glacier. Still enormous piles of sediment that can be deposited once these glaciers start to retreat. Another thing that we can get as a result of glaciation are these so-called kettle lakes. As these glaciers retreat in that zone of wastage, you can have huge blocks of ice fall off the end of that glacier. And when they do, they absolutely have an impact on the surrounding landscape, both directly in that falling in the landscape, but also in the sedimentation that happens around that ice, right, following its deposit in this area. That is, sediments can accumulate around these large volumes of ice, and eventually those large volumes of ice will melt. And so what you're left with is a depression in the landscape. Oftentimes these are very circular in appearance, these so-called kettle lakes. Kettle lakes, that's what those are. All right. All right. Ice is really heavy stuff. Ice is really heavy stuff. So the addition of ice to the landscape actually can take Earth's crust and cause it to reshape, right? This is something that we call isostatic loading, right? Isostatic loading. That is, by adding all of this weight of this glacial ice, we actually get some crustal subsidence. That crust deflects downwards, right? That crust deflects downwards, right? And so in that crustal subsidence there, once that ice retreats, the land surface does not just all at once come popping back up, right? Doesn't come just flying back up to its original elevation. Takes a little bit of time, but it does. It eventually does rise to its previous elevation via crustal rebound. So in areas where we've seen extensive glaciation and those glaciers now removed, we see this rising of the land surface as a result of that isostatic unloading, right? So that's that crustal rebound, right? Isostatic unloading, another term for that. All right. Awesome. And as always, with any of these subjects, again, I'm here and I'm available. If you want to discuss them more fully, you want to learn more about them, you want to make sure you're clear on anything, it's what I'm here for. Please don't hesitate. Please don't ever hesitate to get a hold of me. All right. All right, here we go. So you may be asking yourself, well, all right, Sapmanfield, there obviously have been glaciers at times and then glaciers not at times, right? I know that in places like New York, based on my history class, the places like New York weren't glaciated until just the last few years or so, right? The stories of early settlers and Native Americans most certainly don't include that New York was completely covered in ice up into just the last few years, right? And that's absolutely correct. And so you may be saying, well, then glaciation must vary throughout Earth's history. And I would say that's absolutely correct. And you might say, how? Why? Right? Why? What drives natural glaciation and deglaciation? And I will note, right, that it is not just CO2 levels in the atmosphere, right? CO2 levels in the atmosphere most certainly track with global, with changes in global temperatures, right? And glacial advance and retreat, right? But most certainly that's been the case since long before we started introducing large amounts of CO2 to the atmosphere. So there's got to be something natural that's happening, and there most certainly is, right? And those natural phenomena, right, are these three factors. These three factors, right? That is, or those are, one, we can look at Earth's orbit. You know, if maybe you've constructed your own solar system, maybe for fun or for science fair project or something along those lines, and you've noticed that those orbits, right, that you constructed that with were very circular. And that is that's wonderful, and a great representation of space. But I will note that the circularity of that orbit is not constant. That is, Earth's orbit, there are times when its orbit about the sun may be more circular, right? May be more circular, might have a constant radius, right, about the sun. But most certainly there are times when Earth's orbit is more elliptical, right? That is, there are times in Earth's history where the Earth's orbit will place the Earth further from the sun at certain times and closer to the sun at certain times, right? So that varies through time, right? Another thing that varies through time is actually Earth's tilt. Earth's tilt today is about 23.5 degrees, right? The Earth is tilted, its axis, right, is tilted at about 23.5 degrees. This is what gives us our seasons, right? At 23.5 degree tilt. That tilt too is not constant. Earth's tilt varies through time, goes anywhere from maybe 22 to 24.5 degrees. And that tilt, in giving us our seasons, by making that tilt more extreme, that can make our seasonal variability more extreme. And if we go the other way, if we have less of a tilt, we might have less significant, less severe seasons, which again can impact precipitation patterns and all sorts of interesting things. Another thing that the Earth does is it kind of wobbles a little bit. That is, maybe you've spun a top before and you notice that when you spin that top, especially as it starts to slow down, it has a little bit of wobble to it. That wobble is what is called precession. Precession. And the Earth has a little bit of wobble to it too. Has a little bit of wobble to it too. And just like the Earth's tilt, right, if we change that amount of precession, we can change the severity of our seasons. And really, really important to recognize is that these things are happening, right, in space, right? They're happening in space, in this, what we can think of as a frictionless environment, where each of these three conditions are changing, albeit at relatively constant rates. That is, we can see the rate at which Earth's orbit becomes more elliptical and more circular, the rate at which its tilt varies, the rate at which that precession changes. And we can see that the rate of each, or the rates of each of those things are different from each other, but their rates, the rates for each one are relatively constant. And really interestingly, so are our rates of glaciation and deglaciation. That is, on the same time scales at which this variability operates, and resulting in more or less significant seasonality on our planet, we can see, according to those rates, that glaciation, the extension or reduction of glacial mass on our planet, right, coincides with these three factors directly. This cycling, right, this cycling is something that we call Milankovitch cycles. Milankovitch cycles. These have an enormous impact on glaciation. They have an enormous impact. They are a huge natural driver, right? They are a huge natural driver for glaciation that we can actually see in ice core records, right? That is, in both Antarctica and in Greenland, we've drilled tons of these ice cores, and in collecting those cores, we get this tremendously precise record of climate variability stored in these small bits of trapped gases within those cores, and also within the chemistry of the water itself. We can look at changes in the chemistry of that water and the chemistry of those trapped gases as a proxy for changes in global temperature through time. And we can see this correlation between this Milankovitch cycling and the formation and reduction of glacial ice around the planet. Again, that is not at all to say that atmospheric or changes in the chemistry of our atmosphere can't have an impact, because we see that too. We most certainly see that during periods of extended volcanism, during other events where we have the ability to pump huge amounts, or where the Earth has experienced huge amounts of greenhouse gases being put into the atmosphere, that despite Milankovitch cycling, we most certainly can get some significant glacial intervals, really significant glacial intervals. So that's not to say that this is the only way to change climate, but rather that this is the natural, main cyclical way that we have seen this through Earth's history, right? And it's really, again, important to recognize that there are other factors as well, most certainly, that have had an impact on Earth's climate too. All right, so important to recognize too that we are still considered to be in a glacial period, right? And that's because we have frozen ice, glaciers near our poles. We have continental ice sheets, right, on Greenland and Antarctica, right? Our ice sheets there in Antarctica may be a bit bigger, a bit older. Has to do with ocean circulation around Antarctica and the situation of that continent right over the South Pole, versus Greenland there being a little bit away from that pole and a bit smaller. But we still have these continental glaciers, so that specifies that we are still considered to be in a glacial period. If we had none of this ice, which most certainly has happened over the course of Earth's history, we would call that an interglacial. That's an interglacial period. So if we were to go from our glacial period now to a complete melting of these continental ice sheets, right, that would mean a huge influx of water into the ocean. Sea level variability is driven by changes in global temperatures, both by what water does as it warms up. If you warm up water, it makes it a little less dense. That decrease in density is the result of an increase in volume of that water, which means if you raise water temperatures, it'll be just a little bit bigger, right? You can see this in a water bottle. If you were to take a bottle of water, or a bottle, and fill that plastic water bottle as full as you can get it with really cold water, and then cap that water bottle, then let it sit on the counter, let it come to room temperature, you would feel that water bottle would feel really expanded, right? It would feel really tight, might even bulge out a little bit, right? And that's what, again, ocean water can do too, or what it does, it expands a little bit. But also that sheer volume, that enormous volume of water that's added to the oceans from the melting of these ice sheets, most certainly impacts sea level. We see record of that around the world too. And so under present day conditions, this is what North America, or portions of North America, would look like here with the melting of these ice sheets. So, you know, you're talking about potential impacts to significant numbers of people that live in these areas. All right. All right. So in summary, glacial environments are dynamic environments. They change all the time, right? And tracking those changes gives us an indication both of what glaciers have done in the past in terms of responding to changes in global climate, and thus gives us great insight as to what we might expect for the future. So glaciers move, and as they do, they leave behind these landforms, these tremendous landscapes, both through processes of erosion and deposition. And lastly, that glacial advance and retreat can be directly related to global climate variability as we think about that glacial budget, right? And what we're seeing there is that balance between rates of accumulation and rates of wastage. And so factors including precipitation and ambient temperatures impacts the behavior of a glacier in both of those environments, such that as we see glaciers extend or retreat, that can be a really sensitive proxy for how environmental change may be occurring surrounding that large body of ice. All right, awesome. So as always, any questions at all, if you want to have further discussion about any of this, that is wonderful. If you want clarification, you need anything at all, I'm here and I'm available for you. You are not listening to these lectures alone. I'm here for you if you need anything at all. Please don't hesitate to get a hold of me. I really look forward to the opportunity to chat. I hope everybody is doing wonderful out there. I'll ask that you please take care of yourselves. Be safe, and we'll talk again very soon. Take care, everybody.